Hey guys, welcome to trig number 5 on graphs of sine and cosine functions. Today we're going to look very carefully at these two graphs. We're going to identify a ton of characteristics about them. And then the goal is by the end of the lesson today, you should be able to graph sine and cosine functions as well as their transformations. So let's look at example number 1. The graphs of sine and cosine functions are what we call periodic. And what periodic means is that the function values will repeat as x increases. Now, you might recall from trig lesson number 3 that the sine value of a function is equal to the y value at the corresponding point or angle on the unit circle. Now, additionally, the cosine value is equal to the x value at the same point on the unit circle. And what this is saying is that the terminal side of the central angle on the unit circle creates a point of intersection on the circle. That point of intersection, x comma y, tells you what the cosine and the sine functions are of that angle. We know that the cosine of that angle is the x value, and the sine of that angle is the y value of that point of intersection. So once again, the sine values correspond to the y values on the unit circle, and the cosine values correspond to the x values of the points on the unit circle. Now, with this in mind, we are going to look at the graph of sine theta first. So, example number 1. Since the graph will complete one full cycle in the interval of 0 to 2 pi, the period of y equals sine theta is 2 pi radians. So again, this means that every 2 pi radians, the graph is going to be repeating itself. And that makes sense, right? Because we know one rotation around the unit circle is 2 pi radians, and every time we rotate completely around the unit circle, the sine and cosine values just repeat themselves. So the sine graph has a period of 2 pi, and the cosine graph also has a period of 2 pi. So let's go ahead and graph y equals sine theta, but first I want you to look at the x-axis. Notice how all the points on the x-axis are in terms of radians. This is an easy way to graph because we already know what all of these sine values are equal to. All we got to do is we just got to use the unit circle. So for this graph, I'm just going to copy down just a visual of the unit circle. That way it makes our lives easier as we're graphing. So let's go ahead and start at x equals 0. So if I'm plugging in 0 to the graph y equals sine theta, then 0 is going in for theta. We have y equals sine of 0. Now on my unit circle, 0 is this central angle right here. And we know that this creates a point of intersection 1 comma 0 with the unit circle. So if we have the point 1 comma 0, that means that the cosine of 0 is 1, and the sine of 0 is 0. So since we're looking at the sine graph, I'm going to say, all right, well, the sine of 0 is 0. So I have the point 0 comma 0 on my graph. All right, let's go ahead and move on to the next point. We're going to look at pi over 2. So pi over 2, that's going to be this central angle right here. And this corresponds to the point on the unit circle, 0 comma 1. And since the points on the unit circle are cosine comma sine, that means that the sine of pi over 2 is going to equal 1. So at pi over 2 on my x-axis, I'm going to plot a point at positive 1. All right, let's go to the next one. Now we're going to look at pi. Let's plug that into the function. We are going to evaluate y equals sine of pi. Well, at pi, my terminal side of the angle is right about here. This corresponds to the point negative 1 comma 0. And we know that this goes cosine comma sine. So the sine of pi is just going to be 0. So let's go ahead and plot the point pi comma 0. All right, moving on to 3 pi over 2. 3 pi over 2, plug that into the function. The sine of 3 pi over 2, well, the terminal side of the angle is going to lie right here. The corresponding angle is 0 comma negative 1, and that goes cosine comma sine. So the sine of 3 pi over 2 is just going to be negative 1. So plot the point 3 pi over 2 comma negative 1. Now moving on to the last one, let's plug in 2 pi, the sine of 2 pi. Well, 2 pi is just going to be the same as 0. So we have the point 1 comma 0. So it goes cosine comma sine. The sine of 2 pi is just going to be 0. So we have the point 2 pi comma 0. So as you can see, this kind of creates a little wave, right? We have this curve that is connected and continuous, and it continues to go on forever, all right? So that's what the sketch of that graph looks like. And just note, it also goes on forever in the left direction as well. So that is the sketch of the graph y equals sine theta. All right, so let's move down and talk about some of the characteristics of this graph. First of all, the domain. Well, this graph is going to go forever in the left direction and forever in the right direction. It's just going to continue to repeat itself on and on and on, and same in the right direction. So I'm going to say that the domain of this graph is all real numbers, negative infinity up to positive infinity. Now, the range of this graph, this is actually a bounded graph, okay? And the reason is because we know that the top of this graph is at positive 1 on the x-axis, or the y-axis, excuse me, and the bottom of this graph is negative 1 on the y-axis. And we know that these graphs are periodic, so every interval of 2 pi radians, this graph is going to repeat itself. So the highest the graph is going to go is 1, and the lowest the graph is going to go is negative 1, all right? So the range of my graph is going to be brackets, because we're including positive 1 and negative 1 up to positive 1, all right? Now let's look at the x-intercepts. So the x-intercepts, well, that is, in other words, where the graph crosses the x-axis. And on this little sketch we have right here, we have 3 separate x-intercepts. And as you can tell, this graph is going on forever, so we're going to have an infinite number of x-intercepts. So how do we represent the x-intercepts? Well, notice how the x-intercepts are happening at intervals of pi. We have 0, pi, and 2 pi, all as x-intercepts. So what I can say is, well, x-intercepts are going to be some multiple of pi, or in other words, pi times k, comma, 0. All right, so if we plugged in 0 for k, we get 0, and that's an x-intercept. Plug in 1 for k, and we get pi, that's an x-intercept. Plug in 2, we get 2 pi, and so on. This pattern is going to repeat itself. So we have pi k comma 0, where k is just some integer. All right, so I'm going to say k exists within the integers. All right, moving down, y-intercepts. So looking at the y-intercepts, we notice that, hey, we have the y-intercept 0, comma 0, and that's the only time that this graph is going to cross the y-axis. So I just say 0, comma 0 is my y-intercept. Moving down, let's talk about the maximum of this graph. So when we discussed the range, we found that the maximum is 1, but we want to be a little bit more specific. Where is the maximum taking place? Well, we know that the first interval here from 0 to 2 pi has a maximum at pi over 2, comma 1. And keep in mind, this graph is going to be repeating itself every interval of 2 pi. So what I can say is that, well, if pi over 2 is the x-coordinate of that first maximum, I know that if I were to go another interval of 2 pi, or in other words, add 2 pi times some integer k, that's going to be the next x value for the maximum. So basically, by saying, all right, pi over 2 plus 2 pi k, or some multiple of 2 pi, that's going to bring me to another x value that has the maximum again, because this graph is repeating itself. So at pi over 2 plus 2 pi k, comma 1, we see that we have maximums on this graph. And again, k is some integer. All right, moving down to the minimum. So the minimum, as we said when we were talking about the range, is negative 1, but specifically, where is the minimum happening? Well, on this first graph here, the minimum was taking place at 3 pi over 2, comma negative 1. So what that tells me is that if I were to go another interval of 2 pi, I would find that 3 pi over 2 plus some multiple of 2 pi, or 2 pi times some integer k, comma negative 1, that's going to give me another minimum. And again, k is an integer. All right, let's go ahead and finish off with a couple more characteristics. So first of all, this graph is continuous, all right, because there's no jumps, breaks, or holes. The graph is also bounded above because it can't go above 1 on the y-axis. And it's also bounded below because it can't go below negative 1 on the y-axis, all right? So all 3 of these characteristics apply to the sine function. Now symmetry, this graph has odd symmetry because it has x-axis symmetry, okay? And this is also one of those properties that we found out in trig lesson number 3. We know that the sine function is an odd function, all right? So it has odd symmetry. And now let's look at the key points. Well, looking at this graph on the interval 0 to 2 pi, I know that first of all, we have an intercept at 0, 0. We also have a maximum on the interval 0 to 2 pi at pi over 2, 1. We know that we have a intercept at the point pi, 0. All right, because the graph crosses the x-axis at pi, 0. The next key point here will be the minimum, which is 3 pi over 2, -1. So we have 3 pi over 2, -1. And then again, we have an intercept to finish off the interval. And that intercept is right here at 2 pi, 0. All right, so those are some of the key points that we see in that first interval. And as you know, this is going to repeat itself over intervals of 2 pi in the positive infinity direction and the negative infinity direction. And those are the characteristics of the sine graph. Let's move on to the next page, and we're going to talk about the cosine graph. So the graph of y equals cosine of theta. Now, since the graph will complete one full cycle in the interval 0 to 2 pi, that means that the period of y equals cosine theta is 2 pi radians, just like before. And what this tells us is that the graph is going to be repeating itself every 2 pi radians. So let's go ahead and look at a more condensed interval. Let's look at the interval 0 to 2 pi. So once again, to graph this, I'm going to use the unit circle so I can easily figure out what the outputs of my cosine function are. So let's start on the x-axis at 0. Well, if I'm finding the cosine of 0, the angle has a terminal side right here. The corresponding point is 1, 0, and we know that the coordinates on the unit circle go cosine, sine. So the cosine of 0 is just going to be the x-coordinate, or 1. So 0, 1, I have a point on my graph. Next, let's look at pi over 2. So pi over 2 has a terminal side right here. The corresponding point is 0, 1, and since that x-coordinate is 0, the cosine of pi over 2 is 0. So I plot a point at pi over 2, 0. Let's look at pi. So pi has a terminal side right here that corresponds to the point -1, 0. The x-coordinate is -1, so the cosine of pi is -1. So plot a point right here at pi, -1. Next up, we have 3 pi over 2. 3 pi over 2 has a terminal side right here. The corresponding point is 0, -1. Since the x-coordinate is 0, that means that 3 pi over 2 has a cosine function of 0. So plot the point, 3 pi over 2, 0. Last but not least, we have 2 pi. And 2 pi just brings us back to the starting point, which has a corresponding point of 1, 0. So since the x-coordinate is 1, that means that the cosine of 2 pi is just 1. So let's go ahead and connect these dots. Again, this is a curve, so I'm going to create a curve out of these points. And this is the sketch of y equals cosine theta. All right, so we can see it looks pretty similar to the sine graph with subtle differences. So let's go ahead and move down here. We're going to talk about the characteristics. All right, so first up, the domain of the cosine function. Well, just like the sine function, the domain is all real numbers because this graph goes forever in both directions by intervals of 2 pi. Now looking at the range is the same as the sine function. We have an upper bound of 1 and a lower bound of -1. So that means that the range is from -1 to +1. And we are including those values. Now the x-intercepts are a little bit different. So looking at the first interval, 0 to 2 pi, we have x-intercepts at pi over 2, 0, and 3 pi over 2, 0. So the x-intercepts are still happening in intervals of pi, because to get from pi over 2 to 3 pi over 2, that's one interval of pi. So the way I'm going to express the x-intercepts is I'm going to say, well, we have an x-intercept at pi over 2 plus some interval of pi, which we'll write as pi times k, 0. And once again, we know that k is an integer. And this is just a fancy way of saying, hey, starting at pi over 2, every interval of pi after that, we are going to have an x-intercept. The y-intercept, super easy. There's only one y-axis, and this graph crosses that y-axis at 0, 1. So the y-intercept is very simply 0, 1. Moving down to the maximum. So the maximum is the same. We have an upper bound of 1. So my maximum is going to be 1. However, we need to be specific and talk about where this maximum is taking place. So the first maximum that I see is at 0, 1. We have two maximums on this interval because we also have a maximum at 2 pi, 1 as well. And since this is telling me, hey, every 2 pi radians, there's going to be a maximum, I'm going to say that the maximum is 2 pi, or some multiple of 2 pi, so 2 pi times k, 1. All right, and that totally fits what we've got here, because if we plug in 0 for k, 2 pi times 0 is 0, so that means that our first maximum here is at 0, 1, and then all intervals of 2 pi after and before that. Moving down to minimum, so the minimum of this graph, well, the graph has a minimum or lower bound of -1. Specifically, let's talk about the points where the minimums happen. So the first point that I see for a minimum here is at pi, -1, and we know that this is going to repeat itself. So I'm going to say, well, the minimum here is going to be -1 at pi plus some interval of 2 pi. So 2 pi times k. And the minimum is -1, so I have pi plus 2 pi k, -1. Once again, k is an integer. I'm actually going to include that for the top one as well. K is an integer. All right, moving down to some other characteristics. So for this particular graph, this graph is continuous, all right, because it has no jumps, breaks, or holes. The graph is bounded above, and it's also bounded below, because we have a maximum at +1 and a minimum at -1, and the graph just repeats itself with those same intervals, all right? We have the same bounds for every interval. Now, let's talk about symmetry. So the symmetry for the cosine function is even, and we might remember this from when we talked about trig number 3 and we introduced the functions in the unit circle. And if a graph has even symmetry, that means that it has y-axis symmetry. So it's just the opposite of the sine graph that we talked about on the previous page. Last but not least, let's talk about some of the key points, and specifically I'm going to talk about the interval 0 to 2 pi and some of the key points that we see. So the first thing I see is a maximum at 0, 1, so that first key point here is going to be a maximum at the point 0, 1. Now moving on from that, the next thing I see is an intercept at pi over 2, 0. So I'm going to say the next key point is an intercept at pi over 2, 0. The next key point, after that, we see we have a minimum at pi, -1. So I'm going to say the next key point is a minimum at pi, -1. After that, we do see another intercept at 3 pi, 0. So I'm going to say we have an intercept at 3 pi over 2, 0. And then last but not least, we do have another maximum over here at 2 pi, 1. So my next key point is a maximum at 2 pi, 1. And those are some of the common characteristics of the cosine function. So with that being said, let's go ahead and move on to the next page, and we're going to use the parent graphs of the sine and cosine function to figure out how to actually graph the transformations. All right, moving on to the next page, let's go ahead and talk about some more characteristics of those functions. So looking at the amplitude, we can change the height, or in other words, the amplitude. So amplitude is the same thing as the height of the graph. And we can change it by transforming the equation of the function. And this is going to change the range of the function as well. So looking at the first example, we have y equals 2 sine of theta. Now, historically in this class, we know that any number we're multiplying to our function is our a value. And our a value is what manipulates the vertical stretch or the vertical shrink of our function. So, in other words, we're going to take all of the y values of the parent function and we're going to multiply them by the a value too. So before we get started, let's go ahead and write down the graph of the parent function, y equals sine of theta. Now, if I recall some of the key points of this graph, sine of theta, I know that the first point is 0, 0, using the graph on the first page. My next point is pi over 2, 1. My next point is pi, 0. Then we have 3 pi over 2 comma negative 1 and 2 pi comma 0. And again, this is the parent function of the sine graph. So that is a sketch of what we're looking at. Now, I need to take this function, and all of my y values need to be multiplied by 2. That's going to stretch the graph up by a factor of 2. So let's go step by step to each coordinate on this graph, and we're going to take the y value and multiply it by 2. So let's start with 1 comma 0 times 2. 0 times 2 is 0, so that means I'm still going to have a y coordinate of 0. So 0 comma 0 is still a point on 2 sine of theta. Next up, I have the point pi over 2 comma 1. Now, if I take this y value and multiply it by 2, my a value, I'm going to get 1 times 2 is 2. So my new coordinate is pi over 2 comma 2. So, as I can see, I have stretched my graph by a factor of 2. Next up, I have pi. Pi has a coordinate of pi comma 0. If I multiply 0 by 2, I'm still going to get 0. So pi comma 0 is still a point on 2 sine of theta. Next up, we have 3 pi over 2 comma negative 1. If I multiply this value by 2, I'm going to get 3 pi over 2 comma negative 2. So my new point is down here at 3 pi over 2 comma negative 2. Last but not least, 2 pi comma 0 still has a y value of 0 when I multiply by 2. So I'm still going to have this point 2 pi comma 0. And this is the new and improved graph of 2 sine of theta. So as we can see, all we did is we stretched it by a factor of 2, or in other words, the amplitude was stretched, all right? And that is what the a values do. Now, looking at example number 3b, we have y equals negative 2 cosine of theta. So this time we got two things going on. We got an a value of 2, and we also have a negative. And we know that negatives are going to flip our graph across the x-axis. So what we're going to do is we're going to draw the parent graph of cosine theta, and then I'm going to take all my y values and multiply them by negative 2. Not only is that going to stretch my graph, but it's also going to flip the x-axis. So let's go ahead and start with y equals cosine of theta. Well, using the graph on the second page, let's put some of those key points down. The first key point of this graph is 0 comma 1. Then we have pi over 2 comma 0, pi comma negative 1, 3 pi over 2 comma 0. Then we have 2 pi comma 1, and again, this is the parent graph of cosine of theta. All right, so what we want to do is we're going to take all of these y values of the parent graph and multiply them by negative 2. So first up, I have 0 comma 1. We're going to multiply that y value by negative 2, and then we get 0 comma negative 2. So my new coordinate is 0, negative 2. Next up, we have pi over 2 comma 0. Well, just like the previous graph, if we multiply 0 by anything, we're just going to get 0. So that point stays the same. Then pi comma negative 1 is my next point. But again, I got to take that y value, multiply by negative 2. That's going to give me pi comma 2. All right, so pi comma 2 is my next point up here. 3 pi over 2 has a y value of 0, so that's going to stay the same. And last but not least, 2 pi has 2 pi comma 1. Multiply that by negative 2, we get 2 pi comma negative 2. So that's going to be my next point. And this is what my new graph looks like. So we have a stretch, and we also have a reflection about the x-axis. Now, something to note about both of these graphs. In both examples, the amplitude is 2. In general, we can say that if y equals a sine of b theta, or y equals a cosine of b theta, then the amplitude is defined to be the absolute value of a. So I'm going to highlight that. The amplitude is the absolute value of a. So if I look at both of these functions here, I have y equals 2 sine of theta. The absolute value of 2 is 2, so that means the amplitude is 2. Similarly, we have negative 2 cosine of theta. The absolute value of negative 2 is positive 2, so once again, the amplitude is 2. Now, when a is less than 0, describe the behavior of the graph's key points. So what this means is if we have a negative a value, like we did for negative 2 cosine of theta, the key points, specifically the maximum and the minimum, so the key points or the maximum and minimum, are reversed. And this makes sense because if we look at that second graph that we did, negative 2 cosine of theta, the parent graph had a minimum at negative 1, and the new graph had a maximum. So literally, we just reversed the points, and then we multiplied by 2 to account for the vertical stretch. So we just got to reverse the maximum and minimums when we have a negative a value. All right, so with that being said, let's go ahead and move down to another characteristic of these graphs, which is the period of the functions. So we've already established that the period of a parent sine or cosine graph is 2 pi. And we know this is because one rotation around that unit circle is 2 pi radians. Now let's explore how the general form of the equations can change the period of the graph as well. So here's the deal. Let's look at example number 4a. We have y equals sine of 2 theta. We have a number inside of our parentheses that is attached to theta. So essentially, we are taking the sine of some multiple of theta. If you see this, that means that we are adjusting the period of that graph. Here's how we're going to do it. We know that the standard period of the sine and cosine graphs is 2 pi radians. What we're going to do to find the new period is we're simply going to take the standard period 2 pi and we're going to divide it by whatever the number is inside the parentheses. So since we have a 2 inside parentheses, we take 2 pi radians and divide it by 2. And that is going to give us pi for 1 period. So what does this mean if our period is pi radians? Well, typically, if I were to graph the parent function of sine of theta, we have key points at 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. This is a period of 2 pi radians because it takes 2 pi radians to go through one cycle of this graph. But now, since our period is pi radians, we need to go through one cycle by the time we get 2 pi radians on the x-axis. So what we're doing is we're essentially shrinking this graph horizontally. Now here's the best way that I can conceptualize graphing these adjustments. Since we have a point at every interval of pi over 2, if I take pi over 2 and I divide it by 2 like I divided my full period by 2, essentially I'm multiplying by 1/2, that means that instead of having a new point every pi over 2 interval, we're going to have a new point at every pi over 4 interval. So every pi over 4 is where we're going to plot our next point. So 0, 0 is going to stay the same, but then at pi over 4, we plot our next point, pi over 4, 1. Then at pi over 2, we plot our next point, pi over 2, 0. Then at 3 pi over 4, we plot our next point, here at negative 1 on the y, and then pi over 0 is that last point. And since we have 2 pi radians on this coordinate plane, we can actually go through a whole other cycle of it. So then let's do the next one. We have 5 pi over 4, 1. Then we have 3 pi over 2, 0. Then we have 7 pi over 4, negative 1, 2 pi, 0. And so this is what my new graph looks like. And as you can see, we've adjusted the period, right? Because now, instead of taking 2 pi radians to go through one cycle, we can now go through 2 cycles in 2 pi radians. And that's how we graph the change of the period. Now let's look at example 4b. We have y equals cosine of theta divided by 2. So once again, to find the period change, all we're going to do is we're going to take the standard period, 2 pi, and divide it by the number inside parentheses. Now, theta over 2 can also be written as 1/2 theta. So we're going to divide 2 pi by 1 over 2. And essentially that means we're multiplying by 2. So our new period is going to be 4 pi radians. So this time we are actually stretching the period. So a typical period is 2 pi radians. Now we go through one cycle in 4 pi radians. So let's go ahead and graph the parent function of cosine of theta. So cosine of theta has key points at 0, 1. We also have a key point at pi over 2, 0. Just be careful of your scale factor here. These numbers are written differently. Then we have pi, negative 1, 3 pi over 2, 0, and 2 pi, positive 1. Again, this is the parent function of the cosine function. All right? So now we need to make sure that we account for the period that is 4 pi radians. So what we're going to do is we're going to do exactly what we did before. Now we know that to get from one point to the next on the parent graph, we go through intervals of pi over 2. Every pi over 2 on the x-axis, we're plotting a new point. But since I divided by 1 over 2, what I'm going to do is I'm going to take that standard period, or the standard interval where I'm putting my new points, which, like I said, is pi over 2 typically, and I'm going to take that and divide by 1 over 2, or essentially multiply by 2 over 1. So what this means is every pi on my x-axis, I'm going to plot a new point. So 0, 1 is going to stay the same, but then I'm not going to plot my next point until pi on my x-axis. So pi, 0 is my next point. Then my next point is at 2 pi, and that's going to be -1. So 2 pi, -1. Then my next point is going to be at 3 pi, or 3 pi, 0. And the last point here is 4 pi, 1. And now we notice that we went through one cycle of this graph in 4 pi radians. So the red graph there is the graph of cosine of theta over 2. Now, can you describe what happened to the graphs? The periods for each of these two functions is 2 pi over b. Or what that means is it's 2 pi divided by whatever the number is inside of the parentheses, because one full cycle will be graphed on this interval. So in general, we can say that if y equals a sine of b theta, or y equals a cosine of b theta, then the period is found by evaluating 2 pi over b, or the number inside the parentheses. So now the last thing we got to do here is we're going to compare and contrast what occurs to the period when b is greater than 1 versus what happens when b is between 0 and 1. So let's go ahead and break those down one at a time. If b is greater than 1, which we saw for the first example, if b is greater than 1, that means we have a horizontal shrink. Or in other words, we're condensing that period. So we have to go through cycles of this graph faster. And if we have, so I'm going to say that's the first part. And if b is between 0 and 1, so if we have 0 is less than b, which is less than 1, that means that we are going to stretch the graph horizontally. Okay, so we have a horizontal stretch. So looking at this graph up here, we had cosine of theta over 2. Since b was 1 over 2, and that's between 0 and 1, as you can see, we stretched out this interval even longer. So now it takes longer to go through one cycle of this graph. And that is how we deal with period changes. All right, let's go ahead and move on to the next page. Last page of examples for today. We're going to start with example 5a. Let's talk phase shifts. So a phase shift for a trigonometric function is essentially a horizontal transformation of the graph's initial point. So let's look first at the graph y equals sine of theta minus pi. Now here's the deal. Historically in this class, when we have something such as theta minus pi happening inside parentheses, that represents a horizontal transformation. And with horizontal transformations, remember, we are thinking opposite. So if inside parentheses I have theta minus pi, what that means is I'm shifting my graph to the right pi radians. All right? So if I have negative inside, that means I'm shifting to the right. If I have positive inside, that means I'm shifting to the left. Again, I am thinking opposite. So what I'm going to do is I'm going to take the initial point of the sine function, which I know is 0, 0, and I'm going to shift this to the right pi radians. So my new initial point is going to be pi, 0. And from this point forward, I'm going to follow the same rule that I do for sine functions. The only difference is I'm starting at pi, 0 instead of 0, 0. So now 3 pi over 2, my next point, is going to have a y-coordinate of 1. Then I have 2 pi, 0. And then this is going to be 5 pi over 2, -1. And then 3 pi is going to have a coordinate of 0. So I have found that if I shift my sine function to the right pi units, this is what it looks like. Now let's go ahead and go forever in both directions. So let's go ahead and keep this trend going. From here, I'm going to plot the next point right here at +1. And then I have 4 pi, 0. Let's do the opposite direction as well. So I have pi over 2. Again, if my function is going like this, that means that if I go to the left, I'm going to be going down from pi comma 0. So my next point is pi over 2 comma negative 1. Then I have the point 0 comma 0. And let's go ahead and stop there. We're just going to connect the dots with the curves. And we'll put our arrows to signify that we are going forever in both directions. And that is how we deal with horizontal transformations. So let's look at the next one, y equals cosine of theta plus pi. So here's the deal. If I have theta plus pi inside my parentheses, again, I am thinking opposite when I have horizontal transformations. So what I'm going to do is I'm going to take the initial point of the cosine graph, which is 0, 1, and since I have a shift of 0 plus pi, that means I'm going to shift to the left pi radians. So I'm going to take this point 0, 1, and I'm going to shift it to the left by pi radians. That's going to be this point right here, negative pi, 1. And now I'm just going to follow the same rules that I did before with the other cosine graphs, and I'm going to go through and fill in the rest of the points as if this point was 0, 1. So my next point is going to be negative pi over 2, 0. Okay, that's the direction we go with cosine graphs. Next up, we have 0, negative 1. Then we're going to go back uphill. We have pi over 2, 0, and then pi, 1. And let's do this a couple more times. The next point will be 3 pi over 2, 0, then 2 pi, negative 1. Then we have 5 pi over 2, 0, 3 pi, positive 1. And I'm just going to connect these dots using curves. And let's draw the arrows to show, hey, oh my goodness, that is not what I wanted to do at all, but thank you for your help here. Okay. And that is what my graph is going to look like. All right, guys. And so that is how we deal with our horizontal transformations. Now, in both examples, the phase shift is pi. All right. In general, we can say that if y equals a sine of b theta minus c, or y equals a cosine of b theta minus c, then the phase shift is found by taking c divided by b. Or in other words, we're going to take this number that we're shifting by, and we're going to divide it by the number in front of theta. But in these examples, we didn't have to worry about that, but just be aware this is how you would find the phase shift. So next up, when the argument is b theta minus c, then the phase shift is to the right, all right, because again, we're thinking opposite. And when the argument is b theta plus c, then the phase shift is to the left, because again, we are thinking opposite. So now that we talked about phase shift, let's go down and we're going to talk about vertical shifts, which is also known as midline. So if you add or subtract a number from the entire equation, you can shift a trigonometric graph up or down. I'm going to highlight that, up or down. And this is a shift in the x-axis, which creates a new midline for the graph. So let's go ahead and look at the graph y equals sine theta plus 1. So essentially what I'm going to do here is I'm going to take my parent graph, which I know has key points at 0, 0, pi over 2, 1, pi, 0, and then this is going to be 3 pi over 2, negative 1, and 2 pi, 0. This is my parent graph. And all I'm going to do is I'm going to shift all of these points up 1. And by doing so, I am also shifting my midline up 1. Typically, with these graphs, sine and cosine, we have a midline of the x-axis, right? That is the line that we're working around. But if we have a vertical shift, that means that the midline is going to shift up 1 as well. So sine of theta plus 1, we know that vertical shifts, those are just going to be whatever this number is on the outside. So since I have plus 1, that means I'm going to shift up 1. So my new midline is going to be this line, which I'm going to draw in blue, at x equals positive 1, or y equals positive 1, excuse me. So what that means is all of my points are going to be working around this line. So my first point is going to be 0, 1, because I shift up 1. And now we're just going to do the same thing we did for the other graphs. Next up, I go up 1 at pi over 2. Then I go back to the midline at pi. And then after pi, I go below the midline at 0. Then at 2 pi, I make one full cycle, and I make my way back up to that midline. So this is what the graph of sine of theta plus 1 looks like. And it's going to go on forever in both directions, as we know. Next up, we have example 6b, y equals cosine of theta minus 2. So once again, our midline is typically that x-axis, but if we have a vertical shift here, which in our case is going to be -2, so we're going to go down 2 units, that means that I'm going to take that midline and shift it down 2. So this is going to be my new midline. I'm going to make this a dotted line at y equals -2. All right, so essentially I'm starting at 2, and since the parent graph of the cosine function has a point at 0, 1, since I'm shifting that down 2, my starting point is now going to be 0, -1. And so from there, then I'm going to be working around that midline that I've created. So my next point is going to lie on the midline, which is at pi over 2. My next point goes below the midline, so pi -3. Then I make my way back up to the midline at 3 pi over 2. And then 2 pi radians is 1 full cycle, bringing me back to -1 for y. And obviously, I know this is going to continue in both directions, but this is a sketch of what that graph looks like. All right, guys, and that is how we deal with the shifts of vertical and horizontal shifts. So let's go ahead and go over this last part here. If y equals a sine of b theta minus c plus d, or y equals a cosine of b theta minus c plus d, then the vertical shift of the entire graph is equal to d. The midline of the graph is going to be y equals whatever d is equal to. So if we take a look at this first graph here, since d was equal to 1, the new midline is 1. And for example 6b, since d is -2, the new midline is -2. All right, guys, and that is lesson trig number 5. I hope you guys have a great day, and I will see you back here next time. Thank you.